It's a pleasure to welcome Jay Taylor from USC, and he'll be talking about Broué's Abelian Defect Group Conjecture 1.
Yeah, thank you. So yeah, so this, like Makai said, these next three talks are going to be about Broué's Abelian Defect Group Conjecture. So today, really what I want to do is just get to the point where we can state the conjecture, and I'd like to do a couple of examples just to maybe see what calculations look like for finite groups, the representation theory of finite groups. So that's really the focus of this conjecture. So just to settle up a few things to make sure we're on the same page. So all rings for me are going to be unital. And by an R module, I mean finitely generated left module. And I'll use R mod to denote the category of R modules. And for a module, I'll write it in brackets like this for its isomorphism class. And then we have the R is just the isomorphism classes of all the simple modules. Okay. So I'm sure everyone is very familiar with blocks, but there are a lot of different ways of talking about blocks. So just so we're all clear what I'm going to mean by a block. So I'm going to work over a field K for the moment, of characteristic L, but maybe 0, maybe positive. And let's assume that A is a split K algebra. So throughout this talk, I don't want to deal with division rings and rationality questions. So I'm always going to assume that my algebra is a split. Okay. So for such an algebra, we can decompose it as a direct sum of indecomposable AA bimodules. Equivalently, we can decompose the unit as a pairwise orthogonal sum of central primitive idempotents. So, so this is algebra-wise how we can think about blocks, or we can also think about this in terms of a partition of the simples. So this would be the smallest partition for which there are no non-trivial homomorphisms between simples in the block. And also because my algebra is split, the endomorphism of a simple module is isomorphic to K. And so we also get central characters, and we can say that two things are in the same block if they have the same central character. Okay, so for me, and what's really common in this kind of modular representation theory of finite groups is that the blocks of the algebra are going to be these primitive central idempotents. And then we call the AI, which is what we get when we hit by the idempotent, that's the block algebra. Okay. Okay, so one thing I want to mention here, so the easiest case for blocks is when the algebra A is semi-simple. That means each AI is going to be isomorphic to a matrix algebra over K. Okay, so there's a way we can characterize that I'm going to talk about in the next slides. So one way we can think about that is to say that A is going to be semi-simple if and only if it's projective as an AA bimodule. Okay, so we're going to want to kind of measure in the next couple of slides the failure for an algebra to be projective. Okay, so the focus here is going to be on group algebras. Okay, so I'm going to talk a little bit now about KG modules where G is a finite group. So because we have a group algebra, we can use internal structure of the group to measure properties of the algebra. So one thing you have in the representation theory of finite groups is this notion of relative projectivity. So if you take a subgroup, then you say that M is relatively H projective, if and only if M is a direct summand of the module you get by restricting to H and then inducing back to G. So in this definition, actually, it's convenient to take the restriction of M, but you can actually take any module. Okay, it just has to occur in the summand of some induced module from H. Okay, so this really actually does generalize this notion of projectivity. So if H is the trivial subgroup, then M is projective if and only if M is relatively H projective. And this is pretty easy to see. That's just because if you induce and restrict to the trivial subgroup, that's going to be isomorphic to the number of copies of the group algebra, and you'll get that the dimension number of times. So that means that M has to be a direct summand of Kg, and those are the projective and decomposable modules, are the summands of Kg. Okay, so being projective and decomposable means this. Okay, so what we need for this, so really it's, you know, having this being projective, we can say is being relatively one projective. And so what we have is if you take an indecomposable Kg module, then there's going to be a minimal, a smallest conjugacy class of L subgroups for which M is relatively projective for those subgroups. Okay, so this is called a vertex of the module. So if you're projective, then your vertex is 1. Okay, so with this notion of relative projectivity, we can now apply this to the case of the blocks. So blocks are Kg bimodules, which is the same thing as talking about a Kg tensor Kg op module. Now, because we have a group, if I take the opposite algebra of Kg, well, I can identify that with Kg because I have the inversion map in the group. And so actually, if I want to talk about Kg tensor Kg op, that's the same thing as K of G cross G. So the group algebra or any block in the group algebra can be thought of as a Kg cross G module. Okay. So if I do this, well, this is now an indecomposable Kg cross G module. So because G cross G is a group, I can talk about vertices for the block algebra. Okay, and so I can calculate a vertex inside G cross G, and what's really special is that any vertex is actually a diagonal embedding of an L subgroup. Okay, so all vertices are going to be of the form delta G. Okay, and we're going to call that a defect group. So, all right, so D, defect group. Of the block. And I'm going to define D of E, which is going to be log. So I'm going to look at the power of L that the order of D has, and this is going to be the defect of the block. Okay, so the defect should be measuring how far away my block algebra is from being projective as a bimodule, which means measuring how far away it is from being semi-simple. Okay, so the most complicated block, so if you have very large defect or full defect, then you're considered to be a very complicated block, very far away from being semi-simple. So the principal block of Kg, this is the unique block that contains the trivial module, and this has full defect, right? So what this means is that a defect group of this block is a CELO subgroup. Now, as Jordi pointed out to me in Raphael's ICM talk, he gave a slightly different characterization of the defect group, which is the smallest L subgroup such that the restriction functor is faithful on the bounded derived category of modules. So this is a different way, maybe a more conceptual way of seeing this. Okay, so this, so we're gonna, essentially Broué's conjecture involves the defect group in the sense that it has a relatively strong restriction on the defect group, which we'll come back to later. Okay. So one of the most important things about the representation theory of finite groups is that you can pass between representations in characteristic 0 and representations in characteristic L. So unlike maybe other flavors of representation theory, say if you work with representations of algebraic groups, your field is kind of implicitly given to you because you're always working over the field that the group is defined over. But here, for finite groups, it doesn't matter. We can change the field how we like, and we can try and pass between fields and leverage information between different fields. So we need to actually do this effectively. We need a bit of algebraic number theory. So we have to work with what's called an L modular system. So we're going to take O, a DVR. So a DVR is a local PID. So it's a PID with a unique maximal ideal. So O has a quotient field, and it also has a residue field taken by quotienting out by the maximal ideal. Okay, so the main example here is, so you're going to take O to be the localization of Z, the usual prime ideal. This then has a unique maximal ideal, that's the image of the prime ideal L, and its residue field is going to be just the finite field FL, and obviously its quotient field, that's going to be Q. Okay, so this is kind of the most basic example. And so if we think about by working over the integers and we localize at lots of different primes, we can work over, we can do representation theory for lots of different primes at once. So obviously this example in general is too small. So we need to make generally big K large enough. So I want big K always to be large enough so that the algebras I'm going to consider over big K are split semi-simple. Okay. For other technical reasons, you may want to also take the completion of this. So there's we get a topology, an L-adic topology defined by the ideal that we choose, and then you can complete with respect to that topology. So in this case, if we completed, we'd just get the L-adic integers and QL. Okay, so that we can also do that if we want, and for some technical reasons you might want to do that, but for calculations it's usually easier if I'm not going to do work over the completion just because it's easier. I don't want to have to keep invoking Hensel's lemma all the time, so I'm just going to work over algebraic number fields. Okay, so if you have this L modular system, okay, so I have ring homomorphisms between O and big K and little k. So let's assume that the group algebra, big KG of my finite group is split semi-simple. So one of the most important things about this setup is that, so we're interested in the block decomposition of the group algebra over a finite field, so over a field of characteristic L. Okay, so this little kg. So there we have a block decomposition. Now, what's really important is that every block idempotent in kg lifts over O. So it actually comes from an idempotent over O. Okay, so, and the reason I need to take things big enough is so actually that this is a bijection. So you can always show that it'll lift over O, but to get a bijection, you need things to be big enough. Okay. So if I take a block of little kg, then say B, then I get B star, it's a unique lift of this. So I also get a decomposition of the group algebra over O into a direct sum of blocks. So the B stars are also just primitive central idempotents. Okay. Well, I can also then think of B star as just living inside big KG, and then I also get a corresponding decomposition of the group algebra. Okay. So big KG is split semi-simple, so it also is going to be a direct sum of simple modules, and so each simple module must lie in a unique block of in this decomposition, and so that gives me a partition of the simple modules in characteristic 0 into the blocks from characteristic L. So typically it's extremely hard to actually calculate the block decomposition of little kg because we don't know how to do it. However, we know a lot of information in characteristic 0, and we can actually calculate the blocks, the characteristic L blocks, using information from characteristic 0. So this is typically done by characters. Okay, so I just want to do an example of this. Okay, so let's look at A5. So this is the character table of the alternating group A5, which has order 60. So obviously all the character values are contained in the quadratic field Q adjoins square root of 5. So this is, but this also turns out to be a splitting field for the group algebra. So it's not always the case that the character field is enough to split the group algebra. In this case, it is. Okay, so we want to try and calculate the blocks. So we need to work over the ring of algebraic integers. So the character values happen to be inside the ring of algebraic integers, which is no surprise because that's always the case. Okay, so we look in the ring of algebraic integers. So just like before, we need to localize this ring at a prime ideal, and then I can try and calculate things modulo the prime ideal. Okay, so just like in characteristic L, right? I try and calculate blocks by comparing central characters. Well, I can do that here. I look at the central characters in characteristic 0, and I'm going to reduce them modulo the prime ideal and see if they're the same. And if they are, then those are going to be in the same L block. Okay. Okay, so let's look at this. So let's do. So this is the value, the central character table for the group. So it's pretty easy to calculate the central character table. I just take the size of the conjugacy class, multiply by the character value, and then divide by the dimension, right? So it's the size of the class times chi of g over chi of 1. So that's what this is. This is the value of the central characters. Okay, so let's look at so the only primes that are interesting here, the only cases where the group algebra is not semi-simple, is when the prime divides the order. So the only interesting primes are 2, 3, and 5. So let's look at the prime 3. So a little bit of algebraic number theory tells you that, so 3 is not a quadratic residue modulo 5, which means that this prime remains prime in this quadratic field. So you can just work this is a prime ideal, 3 times the algebraic integers, and then you can work via this quotient. So you just have to now reduce these rows and check which ones are the same modulo this ideal. So you'll get 3 blocks. So you'll get chi 1, chi 4, and chi 5. And then you'll get chi 3 plus, chi 3 minus. Okay, so those are going to be the 3 blocks. So the principal block and 2 other blocks. So this one is going to have full defect, right? So it's the principal block's going to have full defect, and actually these are defect. These have trivial defect, these last 2 blocks. So let's also do this with the prime 5. So the prime 5 is fully ramified in the field. So the prime ideal I want to take is square root of 5 times the ring of algebraic integers. And now we're just going to get 2 blocks. So one containing 4 characters, that's the principal block, and one on its own, the character of dimension 5. Okay, so the principal block has full defect, and the one of dimension 5 has trivial defect. Okay. All right, so let's look at, okay, so what we want to talk about now is a way, so one of the most important parts in modular representation theory, well, let's say this, the first time you approach finite group theory in maybe graduate algebra course, you're going to learn about Celo's theorems. So the first time you want to try and analyze a finite group, you usually look at its L local structure. So you try and look at a Celo subgroup, and you try and analyze by the prime. So we're also going to do the same thing here. So we're basically studying the group by each prime that divides its order. And so you want to know to what extent the Celo or its related subgroups inside the group give information or control the representation theory of this finite group KG. So what would be interesting is, well, let's say I know the representation theory. If I know something about blocks of KG, what can I say about blocks for an L Celo or for L subgroups or for related subgroups like normalizers? Do you want to take a break?
Yes, let's take a break,
Okay.
5-minute break here, and
Okay.
we'll meet again at 3:30. Could you go back to the previous slide?
Mm-hmm.
So the statement is two representations are in the same L block if and only if their central characters are all equal modulo this ideal. Is that right?
Exactly. So what you're really doing, right, is you're just taking, so, I mean, in characteristic L, like if you just forget about characteristic 0 for a second, and you just had these modules in characteristic L, then you would just look at the central characters of these simple modules in characteristic L and then check if they were the same. And that would give you the block decomposition. Mm-hmm. So what you're doing here is you're basically saying, okay, let's look at the characteristic 0 simples, look at their central characters, and then I just mod out by the ideal. So I'm effectively going into characteristic L. And so if I reduce modulo that prime ideal and they're the same, then they'll be in the same block.
I see, thanks.
But it's usually kind of, I don't know, it's very useful that you can, it's very useful that you can do this. Like if you couldn't do this, it'd be very, very hard to calculate blocks. So like almost like it would just be horrific to calculate blocks. Because the other way you can kind of characterize blocks is in terms of the decomposition matrix. But we don't know the decomposition matrix, so that would also not be very, it's always kind of in characteristic 0 terms. So when people say we've calculated the L blocks of for a finite group, what they usually mean is we've calculated the partition of the irreducible characters into and I mean this is hard enough. Like lots of people, I think it's still not completely understood. Like for finite reductive groups, it's not completely understood how you partition the irreducible characters into L blocks. There are still some questions about whether two things actually lie in the same block or not. Because you have to know the character table, and we typically don't know the character table. That's the
it's 3:30, so maybe let's start.
Okay. All right, well, welcome back. Okay, so what we want to do now is try and understand, essentially, is there any relationship between the blocks of a group G and the blocks of a subgroup H? So the group algebra, you can split up. So you can always find, if you have a subgroup H, then KH is always a direct summand of the group algebra. You just take, if you take the sum of everything outside of H, then that'll give you a summand. And you can also decompose KG in terms of its blocks. Now, these two decompositions are decompositions of KH bimodules, okay? So if I think about this as a KH bimodule, then obviously this decomposes in terms of the blocks of KH. So that means that every block of KH, well, it must be contained in a block of KG. Okay, so, but in general, it might be contained in multiple blocks, because the blocks may also appear in here. It could be contained in multiple blocks, and a block of KG may contain no block of KH. So actually, in general, it's very hard to get any kind of relationship between the blocks. But there's a very, very nice situation that happens if you take L subgroups. So this is called Broué's first main theorem, and it has a fancy name because it's important. So if you take an L subgroup, then what Broué's theorem tells you is that if you take a block of the normalizer of your L subgroup, and you take a block with defect D, defect group D, then that's always contained in a unique block of KG with defect group D, okay? And this map gives you a bijection between the blocks, okay? So, you're kind of taking things of, I mean, I guess this is somewhat mysterious. It's not super easy. It's not super obvious how to prove this no matter which way you do it. But one way you can kind of think about it is that is if you think about it in terms of what's called the Green Correspondence. So the Green Correspondence sets up, if you take an indecomposable, so remember these are indecomposable modules for G cross G, right? So you take an indecomposable module for G cross G, and now you restrict down to a subgroup. So when you go to the normalizer, the Green Correspondence tells you that when you take an indecomposable module and you restrict it, you'll get something indecomposable plus a projective. So, and that indecomposable thing that you get is unique. So this is kind of, in a sense, it actually is a special case of the Green Correspondence. So this is kind of a way of thinking about it, but is maybe not super enlightening. But this correspondence is incredibly important. So in general, probably, so what Alperin called the main problem of block theory is to what extent do Broué correspondent blocks determine each other? I should have said this. So let me say this now. So B and BG are called Broué correspondents. Okay, so we want to know to what extent do Broué correspondent blocks determine each other. So what we can kind of look for are numerical invariants that we can keep track of. So one thing we could look at are the number of characteristic L simple modules in the block. Or we could also look at the characteristic zero modules that are also in the block. Okay. Now, we want to talk about dimensions. Dimensions would be pretty interesting to talk about. But one of the problems is if we start we're going to talk about equivalences. And if you talk about equivalences, between blocks, in general, you don't keep track of dimensions very well. So what we want is a relativistic notion for the dimension. So what I'm going to do is I'm going to look at an irreducible character in characteristic 0 in the block. So I can look at the L part of the dimension or the character degree. So the biggest possible thing I can see, the chi of 1 divides the order of G. So the biggest part I can see is the L part of the order. Then what I'm going to do is subtract off the defect of the block. So if I was the trivial character, then I'd be done, right? Trivial principal block has full defect, but then there's kind of an offset, and this offset is called the height. And what's really special about the height is that this is always non-negative. Okay, so you can actually see the defect of the size of the defect of the block, or the defect of the block in the character degrees. And what in general we want to try and keep track of is the height 0 characters inside this block. So notice the height now is relative. The bits of information, the bits of the character degree that depend on the group, this bit and this bit, I've gotten rid of. Okay, so this is the relative part. So probably the first major conjecture in this direction is what's called the Alpern-Makai conjecture. So this says that you take an L subgroup of G and you take a block of the normalizer with defect group D. Then what the conjecture says is that the number of height 0 characters in the blocks, the block and its Broué correspondence should be the same. Okay, so the height 0, the number of height 0 characters should be preserved. So you might have seen this for the Makai, called the Makai conjecture. So the Makai conjecture is more of a global invariant, which is if you took D to be a CeLO P subgroup, then every character in the block has height 0. So what you're talking about is just the number of irreducible characters in the block which have degree coprime to L. Okay, so this is another more global version of this. Okay, so this is still very much an open conjecture, but there is a reduction of this conjecture to finite simple groups, but it's very hard to check. But the conjecture itself is known in very many cases. Okay, so this numerical conjecture about the heights, I mean, it's all very well having numerical conjectures, but really what you want are kind of structural questions or structural conjectures about the blocks themselves. So in representation theory, right, the first kind of equivalences you see between algebras are Morita equivalences, right? So two K algebras are going to be Morita equivalent if their module categories are equivalent as categories. Now, as someone who does a lot of characteristic 0 representation theory, Morita equivalences never quite sit very well with me because they, you know, in characteristic 0, you only keep track of the number of simples and you lose all the dimensions and interesting bits of information. So Morita equivalences are very good. Actually, they're quite strong, but they're relative to the question you're asking. Okay, but one question you can ask is if you have an L subgroup and a block of the normalizer of this L subgroup, is the block, is the block algebra Morita equivalent to the block algebra, the Broué corresponding block algebra in G? Okay, we want to work over O here because we want to keep track of both the information in characteristic 0 and the information in positive characteristic. So we really want them to be equivalent over Morita equivalent over O. Okay. So let's look at an example of this. So I'm going to go back to this example of A5 and L to be the prime 3. So let's take P to be the 3 CeLO, so generated by a 3 cycle. Then the normalizer of P is the symmetric group S3. So we saw there are 3 blocks. So there's just the principal block, which has defect group P, and the other 2 have trivial defect. So remember there are 3 characters, three characters in this block. So what we want to compare it to now, it's Broué correspondent, is the principal block of S3. So actually S3 is, so KS3 is indecomposable as a KS3 bimodule. So there's only 1 block, and it contains the 3 characters of S3, trivial, sign, and the 2-dimensional reflection character. Okay. So this at least shows that in this case, all characters of height 0, so 3 characters on either side, Algebra Makai is correct in this case. Okay, so in terms of the modular simples, this obviously the trivial character restricts irreducibly, and then in this case, if I take the modular reduction of chi4, then that also remains irreducible modulo 3. So there are 2 simple modules in characteristic 3 in this block, and they're obtained just by the modular reduction of these 2 characters. And it's the same on this side. So the trivial and the sign, when I reduce these 2 modulo 3, then they remain irreducible, and that gives me the 2 simple modules in characteristic 3 for S3. Okay. So what I've done here is I've written down characters of the projective indecomposable modules. So when we work between big O and little k, the projective modules, so modules that are projective over big O, those correspond to projective modules over little k. So obviously in characteristic L, we have interesting projective indecomposable modules. Those can be lifted over O, and then I can think about them over big K. So actually I can calculate the ordinary character of a projective indecomposable module. And that's what I've done here. So this chi5, right, if I take its modular reduction, it's going to split as a 4 and a 1. And so this PIM contains 2 copies of chi1, two one-dimensional modules and a 4-dimensional simple module. And its structure as a PIM is pretty easy to write down. It's got to be 1, 4, 1 because the PIM has to be, for group algebras, the projectives are always self-dual. And so here the reverse happens. I get 2 4s and a 1, so the structure of this PIM is 4, 1, 4. Okay. And we can do the same thing on this side, so that reflection character, the 2-dimensional reflection character, that's going to split as a 1 and a 1. So I'm going to get triv sine triv, and here I'm going to get sine triv sine. So this looks pretty good in terms of there potentially being Morita equivalence, right? The projectives look the same on both sides, which is good. So we want to kind of see that there's a Morita equivalence. So the first thing we might try, well, you remember that any Morita equivalence is induced by tensoring with a bimodule. So we have to cook up a bimodule which gives the Morita equivalence. So the first thing you might try is just restricting. So let's see what happens if we restrict the principal block of A5 down to the normalizer. So you can just do this as a character calculation in characteristic 0. So the principal block is the sum of the 2 PIMs. So if I restrict the sum of the 2 PIMs, what I'll get is this. So this is obviously the group algebra of S3. This is indecomposable, and this guy's projective. So restriction actually would, if I was allowed to get rid of projectives, then this would be giving me an equivalence. So it would be giving me what's called a stable equivalence if I was allowed to get rid of projectives. But we're not currently allowed to get rid of projectives. So let's try a little harder. So if this was going to be a Morita equivalence, it would have to send simples to simples. So obviously it sends the trivial character to the trivial character, but what about Chi4, this other simple module? Well, it does send it to the other simple, but plus a projective. So actually, we're pretty close to restriction giving a Morita equivalence. We just have this projective garbage attached. We just have to get rid of it. So what is the bimodule for restriction? Well, it's just BOGBG, right? I just hit the group algebra with the block idempotence on either side. So what's going to happen is that if you decompose this as a bimodule as something indecomposable and something projective. Now, what we can see here is actually this indecomposable module is going to give the Morita equivalence. And you can do a character calculation to check that actually, when you look here, if you tensor the simple module in the 4-dimensional simple in G, you'll actually get that 1-dimensional simple, and then it'll be tensoring with R will give you the leftover bit, the actual projective. Okay, so actually, if you can just take a summand of this bimodule, and you will get the bimodule giving you the Morita equivalence. Okay, so these blocks are actually Morita equivalent. Okay. So let's look at the case L equal to 5. So I'm going to do the same thing. I take a 5 cycle. That's going to give me, and I look at its normalizer. That's going to be the dihedral group of order 10. Okay, so same thing's going to happen again. This the group algebra of the normalizer. There's only one block. So for dihedral group of order 10, there's the trivial, the sine, and two 2-dimensional modules. They're the two possible reflection representations of this dihedral group. And then we already saw that this this block, when L equals 5, there's just a single principal block of defect group P. Okay, so 4 characters on both sides. Algebra and Makai is satisfied. So now let's look again at the projectives. So in this case, things aren't looking quite as good. So what I've done is I've encoded this decomposition of the projectives into what's known as the Broué tree. So the Broué tree is just the vertices of this tree. Those are the ordinary simple modules, and the edges are the projectives. And I just connect 2 vertices with an edge if they occur in the same projective character. Okay, so I've calculated the Broué trees on both sides, and there's something funny here. On here, I've got a character which is a sum of 2 characters, and here I have something which is a sum of 2 characters. This is what's known as the exceptional vertex. Now, there's a theorem of Broué that says that if you have two blocks of cyclic defect, so here cyclic, P is a cyclic group, so if I have of the same size, then they're going to be Morita equivalent if and only if they have the same planar embedded Broué tree. So the fact that the exceptional vertex occurs here on one tree and here on another tree, I know by Broué's theorem that these things actually can't be Morita equivalent. And so what this is really saying is that in some sense, the projectives look different and behave differently here. Okay, so if we look a little bit at this situation, so this the chi one's obviously the trivial character. That's gonna, if I take its modular reduction, that's gonna be irreducible, give me the trivial module. And then these two three-dimensional representations, their modular reduction is also simple. So it's the sum of these two things here would actually, its modular reduction would give me 2 times a simple module. Okay. And these reflection representations, so here, obviously the trivial and the sign, these one-dimensionals, those are going to restrict the modular reductions irreducible. Those are the 2 simple modules in this block. And then these reflections, each one splits in its modular reduction as a sum of 2 simples. So something slightly different is happening on both sides. Okay. So let's try and play the same game that we did before. So let's pretend there is a Morita equivalence. So let's try and get a Morita equivalence by doing restriction. So what happens if I restrict the principal block? So again, the principal block is the sum of these, it's just the sum of these 2 projective characters. Okay, that's the principal block. Okay, and what am I going to get? I'm going to get the trivial plus the sign. So trivial plus the sign, that's going to be the, that's an indecomposable module. That's the group algebra. And then this is a projective, something projective. Okay. Now, if I tried to restrict the simple, the chi3 plus or chi3 minus, I wouldn't really get anything anything interesting. But if I restrict the sum, I get the situation that I had before. I get this ordinary character, so something that whose modular reduction is the simple, and then plus something which is projective. So it's just like the situation before, but now I have to take a sum of 2 simples and not the actual simple. But in some sense, restriction is very close to giving an equivalence. It's just, you can't quite correct by deleting a projective. That's the issue, because you have to take a sum of things. Here you have to take a sum of things where you delete a projective, whereas you just want to take one of them. Okay, so something else is going on in this example. And this leads us to Broué's Abelian defect group conjecture. So Broué's Abelian defect group conjecture says that if you have an abelian L subgroup and a block of the normalizer of D, then it's not that the module categories should be equivalent. It's not a Morita equivalence, but that the bounded derived categories of these module categories should be derived equivalent. So I should say that if you have a derived equivalence between blocks, then you will get what's called a perfect isometry between the ordinary irreducible characters, which preserves heights. So if you know you have a derived equivalence, you know you have a height preserving bijection between the irreducible characters. So you will, this will imply the Alper and Makai conjecture. However, there's a big difference here. I've assumed here that D is abelian, whereas in the Alper and Makai conjecture, there is no assumption that D is abelian. And this conjecture is definitely false when D is not abelian. So we don't really have a good alternative for this conjecture when in the non-abelian case, but at least in the abelian case, this gives a very strong structural explanation for certain numerical coincidences that one sees at the level of characters. So let me just say, I have like a minute, so let me just say, what does this derived equivalence look like? So actually there are kind of stronger things we can say, and we'll probably get onto that in the next talk. Actually, you can say that this is a splendid Ricard equivalence between these categories. That's the stronger form of this conjecture. But what you would expect this derived equivalence to look like is what's called a Ricard equivalence. So in a Morita equivalence, you tensor by a bimodule, which is projective as a left module and a right module. So here you should be tensoring now with a complex of bimodules. And your complex, so it should be perfect, which means it's projective as a complex of left modules, and it's projective as a complex of right modules. And kind of typically what you want is that when you shift, there shouldn't be any HOMs. There shouldn't be any HOMs between the shifted complex for any non-zero I. Okay. So we're going to get on to, I think I've now hit my time. So I think we're going to get onto this more next time. But this is, yeah, so we're also probably going to look at a geometric version of Broué's conjecture. So there's kind of an even stronger form for finite reductive groups where Broué actually predicts what the complex should be that we're tensoring with. But I'll stop there.
Okay, thank you very much. Let's thank Jake.